Well, I'm Daniel, and I'm a senior .NET developer and Microsoft MVP on developer technologies. I'm working with .NET Core pretty much since it appeared, but more intensively in the last 2 years, production work. In the left time, I like to play with IoT and lately with machine learning. And lately as well to contribute to open source projects on GitHub. In the left time, I speak at the conferences at meetups. Well, ML.NET has been designed as an extensible platform. Therefore, you can consume other popular ML models from TensorFlow, Onyx, some other frameworks. The documentation says, and this is how ML.NET is stepping into the deep of learning world. ML.NET is not yet capable of training a deep learning model from scratch. But let's see next minutes what you can do with ML.NET. When thinking of data science and machine learning, Python programming language is making the rules. In addition to that, the existing frameworks like TensorFlow, Keras, Torch, CNTK, you name it, are not easy to integrate with .NET projects. The question is to be or not to be just another machine learning framework. Is Microsoft ML.NET another machine learning framework? I think not. And that's because there are about 6 million .NET developers in the world. I presume not all of them are happy to learn Python, only to find how hard it is to integrate it with their net.work. Machine learning uses algorithms to process data and to learn from data and to make informed decisions based on what it has learned. On the other side, deep learning structures algorithms in layers to create an artificial neural network that can learn and make intelligent decisions on its own. Deep learning is a subfield of machine learning. We know that already. I'm telling that because usually machine learning, it's used for machine learning. ML.NET, it's used for machine learning. But it's not limited to this. And I will try to reveal you what we can do with deep learning. First, let me introduce you TensorFlow. TensorFlow is an open source framework for deep learning and machine learning as well, created by Google in 2015. TensorFlow has support for Python, Java, C++, and even C#. And you can train and infer deep learning models. TensorFlow.NET follows very closely Python naming conventions. So if you like to build a model from scratch, you can consider TensorFlow.NET. Of course, it takes some time to learn it, and you need data science skills. What about if you don't have either of them? Because ML.NET, you don't need necessarily data science skills. Currently, ML.NET is limited to inference, as I said before, and transfer learning. The advantage here is you can use in a very simple manner TensorFlow models trained, built on other frameworks for various use cases like computer vision, image recognition, voice recognition, language translation, and more. Nevertheless, training a deep learning model from scratch, it may take maybe several days or weeks or even more, depending on your computing power. But it's not always the case. For example, you can do inference on images using TensorFlow inception model. I will let you know in a bit what's inception model, which is a frozen model saved in protobuf format, a file basically. And this model is used for image classification. It was pre-trained with millions of photos of different objects like animals, vegetables, and other things you can find in day-to-day life. And there are about 1,000 categories, 1,000 classes. And the model will output the most similar class for your image along with their score. So it will try to make a guess, the best guess. In the first line, okay, let me go next. So as I said, ML.NET is supported only for inference or for predictions, but how? But by using transfer learning. There are a lot of models, and it can be very useful if you want to integrate AI into your projects, adding a few NuGet packages and calling a few methods in C#. And now that's inception model. It's a convolutional neural network, 48 layers deep. Doesn't mean too much for me, and I guess not for all of you, but doesn't matter. We can load a pre-trained version of the network trained on more than 1 million images. And that's able to classify images into 1,000 object classes categories, as I said before. You can actually, the model is using images in a resolution of 299 by 299, but that's not mandatory. It will be, our code will resize the image to the desired dimension. Well, what's transfer learning? Transfer learning is a machine learning method where a model developed for a task is reused as the starting point for another task. Simple. There are a lot of convolutions of layers. Some of them we are using as they are, but some other part we might be able to change. We will see later when we will examine the model and we will see the code. Please notice in this image the diagram with the layers of TensorFlow, and only the latest dot, the blue dot there, is the part which we will retrain or actually do by ourselves, and we will reuse the rest. Because the last part, it's the classification. Okay, let me make an analogy here. We might have brains to figure out basic shapes, to figure out curves, lines, to figure out parts of the objects, more complex parts, for example, eyes or feathers. And that's knowledge. But if we want to use these brains, these, I don't know how to call it better, these muscles, to leverage these for other images which were not used primarily for training all these models, we can do that. Why? Because basically a dog or another fantastic animal, they are the same. They are the same in terms of shapes. So what we need to do it is to refine the latest layer of this. Yeah, that's the layer which we will retrain. Actually, it's not retraining, it's like putting away this layer and replacing with our knowledge from our data. Like that one, responsible for identifying the concrete objects. Let's take a look on the code. We will have a demo later, but first let me explain you here something. That's all the code we need to load the model, to build or to predict, to train the model, to retrain the model, and to predict the data. It's no more. Of course, we can make it more complex, but it's enough to solve our problem. And we can see there first, in first line, we are loading the model. Actually, here we are not loading the model. We have here an instance, an empty instance of an object, but we need it to read the schema of the data. And then we load images, we resize them, extract pixels, and then we are dropping these images into the model. That's the pipeline. When we are dropping this into the model, the data is traveling all the way down to the latest, to the output. And the latest layer, the last layer, it's softmax. Well, softmax is a classifier, but it's classifying our original 1000 classes. And then, having this model, we call fit method in order to train the new model. And then we can start predicting data. How can we do that? Dropping new samples, new images inside the prediction engine and predicting data. Let's take a look on the layers. Actually, it's the latest part of the entire model, but I have here this fantastic tool called Netron. Netron is able to show all the layers, and it's compatible with many frameworks, including TensorFlow and ONNX. So we have here, I don't know, maybe 48 layers, starting from the input. And then traveling down to this softmax layer, which is sorting, which is choosing from 1000 classes which one it better fits the prediction. Let's go back. In case we are not pleased with the capabilities of our original model, we can change this part, but let's not anticipate too much because Netron, it's ruining my demo. Actually, not the demo entirely, but the presentation, because it's showing in advance. Well, we are here. We have now pretty much the same code, but instead of stopping at softmax layer, we are stopping one layer before. It's softmax pre-activation. Let's go back. So it's not here, but it's here. And that means we are not relying on those 1,000 classes, but instead of that, we are relying on the brains of our model. Well, in addition to that, we have to do more. Now, for example, we have images for training in the data location here. It's not an empty instance as it was before. Now we have data because this data, it's finishing our job. It's finishing the training with our new classes, which we plan to use for our problem. For example, we might have 2 classes at least, right? But we might have 100, a dozen, doesn't matter. But we have to provide enough classes, and that's not too much. I will show you my demo. It has horrible little images, but it still does the job. So after we are calling this, we still have to do something by hand. It's calling the multi-classification trainer, LBFGS, but it's not necessarily this one. We can use any other algorithm trainer which is doing multi-classification. Of course, the accuracy will be a little bit different, but we have to choose which one. Maybe we don't need the best, the most exact one, but we need the fastest one. Let me put them side by side. In the left part, we have the original model, and in the right part, no, it's vice versa. In the left part, we have the transfer learning for our model, which we shaped by using new data. And in the right part was the original model. So it's not much longer, but we have to code the labels to numbers. That's why we are calling map value to key in addition to the right part. And then at the end, we will do the opposite, map key to value, to reverse back the numbers to labels. In that way, we will see the names, the friendly names, not numbers. It's not funny to see, okay, our model returned the object 2031. No, I have to see, and we did it by purpose.
Daniel, are you okay if I ask you a question now, or you prefer to wait till the end?
Please do that now. Please do now.
There is one question in the chat saying how big in Hugh is saying how big in data size is a typical model that incorporates all that learning, e.g. the classification one you mentioned for 1,000 categories of picture.
In Inception, it's not a very large file. It's only 53 megabytes. And usually such kind of models are below or around 100 or 200 megabytes. Not very large. This was the question, or
yeah, I think that was the question. So it's mostly the time that it takes to train rather than the size of the data. Yeah. Thanks.
Cool. Welcome. Well, if we talk about the size of the images which we plan to use for finishing the training, that has to be too much, because if you remember, the resolution is 299 by 299. So that's not very high, not very large file. So, but anyway, we better have a few dozens for each category at least. And for example, we can take the same picture for the same object by different angles. And that way we can trick the model. We have multiple objects. Anyway, the professional teams are using some small rotating platforms, and they put on that platform the objects, and they are doing repeatedly the pictures. Anyway, so to resume, what's different here? Because usually I'm learning by seeing the differences. I'm like the octopus, or no, there are some animals on the bottom of the sea which are sensing only the move. The frogs are sensing only the move, right? Well, we have to have data if we plan to train ourselves, and we have to stop earlier. In addition, we have to map the value to key and the key to value, and to call a classifier. That's it. Let's see the demo. First, let me show you. I have a class for...
We can only see the slide at the moment.
Oh, really? Oh, why is that? Thank you for letting me know. I will try to reshare. Let me try to reshare. Maybe I have shared the client window instead of the screen. Stop share and share again. What about now?
Yeah, you can see the code.
Excellent. Well, so here is the part where we build and train the model. And of course, we have a lot of C# statements to measure the quality of the model and to send the response to the API. And after that, I'm using, but let me show you the interface. After that, I'm using a minimal interface built with Bootstrap and jQuery. And I have prepared here a few images, but the interface, it's not very efficient. I mean, it doesn't know to add new images. I have to add them by hand because I have invested the time on the most important part. But let's pre-select here this dog, and I will hit score image or predict. And it says it's a Maltese dog, 99%. But it's not unsurprisingly, because it's obvious it's a dog. If it's obvious, usually it's obvious for the machine learning as well. Let's try this giraffe. Well, now we have a few problems because, and that's pretty normal. I mean, many people on this planet will think this is a cheetah, but it's not because the mistake. It's because it seems pretty the same, and there is a problem with the model. The problem it's getting square images. So if the image it's rectangle, or it simply ignores if the image is not square. So that's why this is a weak part of inception model. The objects which are not very proportional, they tend to look the same. Let's try this lighter. It's a lighter. That's nice because it's true. And it's a candle because it's a flame here. Or maybe a torch. It's very good. Let's try this penguin. Yeah, no problems. Let's try the match. No problems. That's the original model. But let's try with our images. So forget about all these classes and bring our images to fulfill the training. I have used these pieces from my daughter playground. And you can see there are only 5 of this class, the Hello Kitty. And then there are a few ponies, and then a few Lego, wooden parts, and that's it. Not too much. Actually, it's horrible little. I should have put more because I still have some errors. But anyway, it's doing pretty good job. But please bear with me because I didn't do my homework very well. I will leave this open because I want to show you something. So having this, I will fulfill the training. Let's wait a little. And done. Now we have a new model which is able to detect our classes. I will use the predefined, for example, this wooden piece. Predict. Of course, it's wood because I train with woods. Let's use this. It's unicorn, and this is pony. You know the difference, right? It's, if you have kids, this is crucial. And that's Hello Kitty, which is 96. But now, let's see how it's behaving with other pieces which I didn't use for training. Well, I will ask you to trust me. I have here a mini studio for mini pieces. So I have this, my computer connected to a Raspberry Pi, which is taking pictures. That's it. But let me capture the object which is now in front of the camera. It's a Lego, right? Now let's try to predict. 63, not bad. Let me try to put another Hello Kitty. Okay, I just changed the subject. Scanning. So this Hello Kitty, it's another one. Not the same. Yeah, it's more pink, whatever. I'm not good at that. But anyway, it's 61. Now I will put here a giraffe. I didn't use a giraffe for training, but let me try. At least it's a pony, it's not a Lego or something else. Actually, it's a Lego, but we don't care now. And I will put another pony here, which the same, it's not used. It's a unicorn, right? But the angle, it's not the best. So that's why it thinks it's a pony. Let me fix the angle. And now I think we will have a few problems. No, it's fine. But a couple of hours ago, it said it's Hello Kitty, which is not. Ask my daughter. Well, for now, the demo says we can use the model to create critical tasks. Okay, this one is critical if you ask me. I have a lot of toys which I'm not knowing by the name, but yeah, that can be a problem, but can be used for fantastic projects very easily. So if you are .NET developer, you have no excuses now. It's so easy. Let me go back to the presentation. And let me tell you the other way of using models created with other frameworks, and that's Onyx. I have to admit, first time I had the feeling it's from a fantastic game, but it's more. Onyx is a standard, interoperable and open format, and is created by Facebook and Microsoft, adopted by Amazon and other big players. And with Onyx, AI developers can easily move models between the frameworks. You can save as Onyx and load as Onyx from another framework. Virtually all important frameworks have converters. So Onyx is a portal format. And that's fantastic because we can use a huge zoo. That's how they are calling these collections of models, zoos. So we can use models from any platforms as far as it's in Onyx format. I'm very curious about, right now, about some speech recognition, and I'm still looking for one which I can use in .NET. Why I cannot use this yet in .NET? It's because I'm lacking knowledge about Onyx and about TensorFlow. And I think for that reason, I have to study a little because I simply don't know how to prepare the model, how to set up the model with the initial parameters. Some of them are waiting for values, for coefficients, for arrays, and I simply cannot figure out how to put them there. But soon, I guess. Anyway, I have managed to use a few, some other image recognition models, but that's not fun. We have already. I have used one which plays chess, so we can predict movements. It's interesting. Let me tell you a little. Yeah.
Daniel, there is a question from the audience. Is there a way to debug or tracing as the model runs to see how the model works, or is this just a black box?
It's a black box, and I will tell you why. ML.NET is working natively with data views. So data views being lazy loading objects, you cannot stop the whole process and see what's in the middle of the pipeline. So yeah, debugging it's ugly. I have to admit that. And usually it's a pain. I don't know some other way, but there are a few guys which I suggest you to follow, which you can find related to ML.NET. It's John Wood, it's Alex Lott, Luis Quintanilla, Brie Altman. These guys are bringing news all the time, and the things are changing fantastically. I mean, 1 year ago, many things we didn't have for ML.NET. For example, now we can work, we can train, we can experience with the model in Jupyter Notebook with .NET kernel. And we can open that Jupyter Notebook in Visual Studio Code. And we can now make inference in Blazor. And that's fantastic. I just can't wait to load data from my Raspberry Pi, even if it's a browser. But I was so needing to see I can use a Raspberry Pi to do machine learning. Of course, it's not doing inside the process server side, right? Not yet, at least. But you can do that with a single Raspberry Pi and call the content from a browser anywhere. And that's possible now. I will tell you a little bit later a few details about this. Now, coming back to YOLO model, well, the same as Inception, which is not a dream in a dream, YOLO is not a pizza master, right? But it's something else. It's an acronym for you only look once, and it's very known deep learning model for real-time multi-object detection. And it's doing that in real time. I mean, it's above 30 frames per second, depending on the machine. On Raspberry Pi, maybe it will not be 30. On CPU, because if it's able to use GPU, it's even faster. And it's able to identify 80 classes. It's not 1,000, but you know, when you are driving, doesn't have to be 1,000. 80 classes, it's pretty good, because the objects usually they are normal to be there on the road. But there are larger versions like YOLO 9000, and it detects now 1,000 classes, and that's huge. There is another YOLO, it's YOLO, Tiny YOLO, which can detect 20 classes. And this is what we will use for our demo. But it's able to detect only these 20 classes: a person, a bird, a cat, a cow, a dog, a horse, a sheep, an airplane, bicycle, and so on. But that's pretty much normal to see this on the road. Well, except well, the TV, it's odd. It's not, because maybe it's an advertising, right? And Tiny YOLO, it's really fast. Even for a Raspberry Pi, it can run real time, because usually it's over 100 frames per second on a regular computer. And I'm telling that for a couple of years now. I have this slide for a couple of years, but the computers are still evolving, right? I guess. Now let me show you the code. The code, it's not very different. Again, loading an empty instance just to read the schema, and then loading images, resizing, extracting pixels, and then applying ONNX model. You can see it's less than what we can do with TensorFlow. I don't know why is that, but it seems like we are more limited. But anyway, we can consume, we can do inference, but we cannot do transfer learning. That's for sure, at least for now. From the coding perspective, yes, the loading, the building, it's smaller, but there is more code in getting the meaning from the response, because I will try to show you, because now we have here a different approach to extract images. Even if object detection, it's pretty similar with image recognition, object detection, it's able to detect layers over other layers, because it has a way to divide the screen in 13 by 13 areas, and then trying to detect objects in each of them. It's complicated. I'm not expert, and I cannot tell you exactly what happens, but I can tell you this is for identifying multiple objects. So from the coding perspective, yeah, it is more complex to get data from that image, but no, not rocket science. With Netron, the same, we can open the ONNX file and see what's in it. Some of the models are reporting more details about who created this model, some description, license, but the more important it's the input and the output. For example, we can guess here in this tensor, this is a tensor, we have an image because it's a matrix by 3 green, red, and blue colors, channels, and for 416 is the resolution. And what's returning? Well, it's dividing the image in 13 by 13, and it's using an index here to identify the object. Let me show the last one. It's layer, it's grid. The name is grid. I'm showing you this because maybe you will be tempted to hack some other models. What I did, it was very interesting for me to try to find new models which I can use in my applications. So we can see here the grid as an output column, and the input column is an image. That's correct. It's an image. Which image we can find it here, but then the image is resized, and then some pixels are extracted, and the ONNX model gets only the numbers. But the rest is the same. Fit for building the model and create prediction engine, and then do the predictions. I will show you in the demo in a bit. So we load the image, the model, which the YOLO model, which is, as I promised, very little code. It looks to be even little, but it's this trick I forgot to split. Like this. Now it looks pretty similar. And then we are calling create prediction engine and returning the prediction engine. later we are predicting in this method the data. When we are predicting the data, we have everything there, everything which was detected by YOLO. But we might want to decide what to keep, maybe to set a threshold and to put a maximum number of objects in the image. And very important, to return the box which gets the image in order to locate it in our image. Well, we are close to an end, but I want to tell you a few words before. ML.NET is not going to replace existing frameworks like TensorFlow, but considering the AI is going to be adopted by the majority of the applications, as .NET developer and not having a data science background, I prefer code-first approach. And ML.NET is code-first approach. It's open source, it's many things, but I like this a lot. It's code-first approach. I'm not a data scientist. ML.NET is very easy to learn, and you can use it on premise, on different platforms, even in cloud. But I like cloud, but I cannot admit we depend on cloud with everything. For example, my Raspberry Pi is not in the cloud, right? At the end, some good news. Blazor does a wonderful stuff with ML.NET, and I have experienced with inference for now. So having a trained model, I can consume this model and make predictions. Indeed, there is a limitation. That's why it's working only for inference for now. I'm not saying about deep learning only, right? I'm talking about machine learning in general. So it shouldn't be only inference. But in Blazor, you cannot use to build a model. You cannot build a model under Blazor because it's using JavaScript. And JavaScript is single-threaded. So the guys from Blazor managed to solve this problem with the single-threaded thing, but only for inference, for now. I think they will be able to adapt some trainers for single-threaded model, but it's just a guess. Usually we don't train in browser or on IoT, right? But we want to consume models and do AI. Well, that would be all. And if you have questions, please hit